First of all, let me introduce Professor Wilczek. So just a short introduction. Professor Wilczek received PhD in physics in 1974 at Princeton. During his PhD, working with David Gross, he discovered asymptotic freedom, which plays an important role in quantum chromodynamics. So I wouldn't list all the fellowships, just a couple of them received by Professor Wilczek. So Mark Arthur Fellowship, a member of the National Academy of Sciences of the United States, American Academy of Arts and Sciences, Lawrence Medal, Lillian Field Prize of American Physical Society, High Energy and Particle Physics Prize of European Physical Society, and eventually Nobel Prize in Physics for the discovery of asymptotic freedom in the theory of the strong interaction. So currently, Professor Wilczek holds a Hermann Feshbach Professor appointment at MIT, Center for Theoretical Physics. He's also affiliated with Shanghai Jiao Tong University in China, Arizona State University in the United States, and Stockholm University in Sweden. So in his paper published in Physical Review Letters in 1978, Professor Wilczek put forward the concept of Axion as a possible solution to a strong CP problem in quantum chromodynamics. So later, the Axion became the candidate for dark matter, and today Professor Wilczek will tell us about further advances in this field. So the talk on axions and the dark matter problem. Please, Professor Wilczek, you are welcome.
Okay, thank you very much. So axions have become a very large subject with many facets, as you'll see. I won't be able to go into significant depth on all facets in an hour or so, or 45 minutes, but I wanted to introduce you to the subject so that you could make use of the large literature and be oriented in it. And I think share the sense of excitement that's now really bubbling up in the physics community. Axions have the unusual feature that the number of citations of the basic papers has gone up year after year since the subject began. Now, so here is a breakdown of the subjects I'll discuss. I've organized this into 5 sections. Some of them are quite short, some less short, but I will discuss why fundamental physics needs axions, what they're, I would say, probably the best motivated extension of what's called the standard model in physics. I'll discuss then the properties of axions regarded as particles, things like their mass, their spin, and their interactions. I'll discuss why cosmology needs some hitherto unidentified new form of matter in order to describe the universe as we observe it, the so-called dark matter. Then I'll discuss how axions, which were invented for quite a different reason, turn out to be excellent ingredients to make the dark matter. And then I'll kind of switch gears to discussing the phenomenological effects of axions that could lead to their identification or not as the dark matter. I'll discuss astrophysical consequences of the existence of axions, laboratory experiments where you see the effects of axions without looking up to the sky or depending on the universe to provide them. Then I'll discuss the exciting frontier of trying to detect the cosmic background of axions, which would provide the dark matter. These are called Axion haloscopes. Halo here refers to the halo of dark matter that surrounds our galaxy. So this is meant to detect the axions that make up the dark matter halo of our galaxy, if indeed they do. And then finally, I'll talk about generalizations of the concept of axions, basically use of the same ideas and equations to describe properties of certain condensed matter systems, quasi-particles within condensed matter systems, and also extensions of the ideas of axions that have appeared in the literature that use the same word for different things. I just thought I should warn you about that. Okay, so as I said, I won't be supplying details on this vast array of subjects, but you can find a very authoritative review, especially authoritative with regard to supplying an enormous number of references in the particle data group. And this has also numbers and as the subjects that it doesn't cover, of course, you can follow up by clicking on the references and doing Google searches and so forth. So let's get into the heart of things. Why fundamental physics needs axions. And I think it's instructive and entertaining to introduce this motivation, this explanation of why axions are needed by asking a theory of why questions, a series of why questions. So few aspects of experience are as striking as the asymmetry between past and future. The past is very different from the future. We remember the past, we make guesses about the future, and so forth. And if you run a movie of everyday life backwards, it does not look like everyday life. So here's an example of that. You would be very surprised if you saw that happening. And yet, time reversal symmetry, usually denoted by the letter capital T, was a notable property of the fundamental laws of physics for several centuries, starting with Newtonian mechanics and continuing through general relativity and quantum electrodynamics well into the 20th century. This was not only mysterious, but also problematic in a way, because it gave rise to the issue of how you reconcile fundamental laws that have this symmetry with the description of the world that doesn't appear to have this symmetry. This is the famous problem of irreversibility in statistical mechanics. But you can also, there's also a problem in the other way. Why, if the goal of science is to describe the world, why do the laws have this feature which make a problem in describing the world? So why? Now, as long as this symmetry of time reversal in fundamental laws appeared to be an exact feature of those laws, it wasn't clear that asking this question was a fruitful question, would be fruitful. The end of a series of questions has to end somewhere. If you've ever interacted with a child, you know that they can keep asking why forever, and eventually you just say, that's the way it is, or put the child to sleep by extending the discussion for a long time. But in this scientific context, it was a possibility, it would have been a very real possibility, that if the symmetry were exact, we would just say that's the way it is. It's rock bottom. That would be a satisfying, nice feature of the world. It has some extra symmetry, and that might be just the end of the story. However, in 1964, James Cronin, Val Fitch, two experimental high-energy physicists, and their collaborators discovered a subtle effect in the decay of unstable particles, K-mesons, that slightly violates T-symmetry. And so this idea that T-symmetry might be rock bottom is just not true. So why? So we're left with, why should you have this principle that we don't need to describe the world? That's kind of an embarrassment. And yet, even worse, it's not even true. Exactly. And this has led to many investigations in fundamental physics and remarkable progress worrying about this problem. And by now, we've almost nailed it, I would say. We've almost got a very satisfying explanation of why the laws of physics are almost, but not quite, invariant under the change of the direction of time. And it's the following. The basic sacred principles of modern physics, sacred comes with an asterisk. I'll elaborate on that in a moment. Anyway, the sacred principles of modern physics, namely relativity, quantum mechanics, and the kind of local or gauge symmetry that goes into formulating the very successful standard model, these sacred principles are very powerful. They highly restrict the possible forms of interactions. So if you want to satisfy those principles in the way, at least in the ways that we know how to construct embodiments of all those principles, the possibilities are very restricted. And two Japanese physicists, Kobayashi and Masukawa, basically showed that there, within the standard model of particle physics, once you expand it to include three families of fundamental fermions, at the time they did this work, there were only two, but they predicted there would be a third, and that turned out to be true. That if you, in that version of the standard model, which is the currently accepted one, there are two possible sources of T-symmetry violation that are consistent with the sacred principles. One of them beautifully explains what Cronin and Fitch observed, and a lot more. In the years since, people have studied not only K mesons, but things called B mesons, and a very large number of different phenomena involving their decays that exhibit T violation. And there's a very beautiful theory of that based on the one of the possible sources of T-symmetry violation that Kobayashi and Masukawa identified. But the other is an embarrassment. It doesn't happen. If it did, or it doesn't happen with very high accuracy, if it did, if there were interactions, the second kind of allowed T-violating interaction, it would induce what's called an electric dipole moment of nuclei that would be far larger than experiments allow. In case this is unfamiliar, let me just say that an electric dipole moment of an elementary particle is an electric dipole field whose orientation is whose axis is set by the direction of the spin of the particle. So the spin of a particle would induce an electric field, and that's not observed to happen with very high accuracy. Many very sensitive experiments have been done to look for this effect, and it has not been observed so far. Whereas, for instance, the corresponding magnetic effect, which does not violate T-symmetry, the magnetic dipole moments of nuclei and elementary particles in general, are a thriving industry of experimental physics, where people use accurate measurements of those things to diagnose fundamental laws and also the properties of atoms, nuclei, and molecules, and so forth. So why? Why does this second interaction not happen? Oh, and I see there is a question that maybe I should address. I've talked about T symmetry, that is time reversal. Often in the literature, you'll see the same kind of phenomena described as involving CP violation, where C is charge conjugation symmetry that changes particles into antiparticles, and parity is a spatial inversion. There are very good reasons, sacred reasons, to expect that the combination CPT is always a valid symmetry. It's highly connected to the relativity and quantum mechanics, and given, if we assume that, then CP symmetry, violation of CP is uniquely connected to violation of T. So I use them interchangeably. And maybe at this point, I should also say a word about the asterisk that appeared on sacred principles. Of course, in science, nothing is sacred. What I mean by sacred principles when I speak of relativity and quantum mechanics and local gauge symmetry is that these are principles that have been so fruitful and verified in so many ways, direct and indirect, that if we found violations of those things, we'd really have to unlearn a lot of what we think we know. And that would be much more disturbing than giving up on T symmetry. Or so we have to start with some things that we use as foundations, and those are much more secure foundations than just asserting that T symmetry interactions are small or not small in different cases. Okay, so we've almost but not quite nailed it. We've gotten almost a beautiful explanation of this remarkable fact that T symmetry is approximately true but not quite true, but there's one loophole remaining. Now, in the past 40 years, there have been several attempts to explain why, to close this remaining loophole, but only one has stood the test of time. That is, we have an unwanted coupling, an unwanted term in the fundamental laws, an unwanted term in the Lagrangian of the world as it's formulated, an unwanted term that comes with a coefficient, a so-called coupling constant. What the leading theory that explains why it's so small is to promote that unwanted coupling constant into a dynamical entity. So instead of a constant of nature that's fixed for all time, whose value is small by observation, but not theoretically, it's not explained theoretically why it's small. We promote it to a dynamical entity in a framework in which the preferred value, the energetically preferred value of the coupling is 0. So then the idea is that over the history of the universe, it evolves to 0 because it's not fixed as a constant of nature, sort of outside the domain of physics. It's not an eternal number, a coupling constant, but rather a dynamical entity. Now, in the context of quantum field theory, in the context of modern fundamental physics, when you have a new dynamical entity, it's got to be a quantum field, and associated with any quantum field are the quanta of that field, the particles in which it creates and destroys, the excitations that motion of the field supports. So the new field that you need to solve this problem has very particular properties. It's a new kind of particle, and I named it the Axion in homage to a laundry detergent because it cleans up a problem in fundamental physics. Now, this basic idea goes back to two physicists named Roberto Pache and Helen Quinn, that you should promote the coupling constant into a field. They didn't really address the theory of the idea that you need a theory of evolution to explain why it evolves to zero. They just assumed that the energetically favorable value would somehow emerge. In any case, and that's a very important feature, as we'll see, that the fact that it evolves, that's what gives you the dark matter connection. But we'll come to that. In any case, assuming that it does evolve to zero, it does evolve close to the energetic minimum, that otherwise mysterious coincidence that the coupling is that potentially the extra coupling that potentially violates T-symmetry is observed to be very small in nature, gets explained because it's not a constant of nature. It's something that can respond to conditions in the universe, responds to dynamics, and therefore, if it wants to settle down to zero, it will. Here's a picture that goes with those words. That's very instructive. So you have a field. You should imagine this picture happening independently at every point in space and time. This is a picture of the internal space of the crucial fields. So there's a field which has a value in the early universe, starts somewhere, and the value of this field is the coefficient of this unwanted interaction, and the energy landscape for this field is what's depicted here, and it has a kind of flat direction where the energy changes very little, but it also has a systematic direction, and it rolls down as the universe evolves and gradually settles down. There's a slight tilt in the field, and the field settles down to a value where that unwanted coupling vanishes. But the important thing, the subtlety that's very important to recognize here is that because there's a nearly flat direction, a direction that's associated with very small changes in energy, the quanta of that direction will be very light particles, and those are the axions. So this is how the theoretical scheme that solves the problem of explaining why this unwanted interaction doesn't occur leads as a byproduct to the existence of a new kind of light particle, the axion, with remarkable properties. So let's discuss what these particles are. Their basic properties of mass, spin, and how they interact with other forms of matter. They also interact with themselves, but those interactions are very small. So I won't discuss those. So because axions are so closely tied to symmetry and its breaking, I mean, I haven't gone into the mathematical details of how this theory is constructed, but it's very constrained in order to do the job that it's meant to do of addressing why, I mean, why the coupling settles down, because you want the dynamics to evolve in just the right way. You have to postulate a kind of symmetry, and that symmetry constrains the interactions of the axions very much. So much so that basically, for most practical purposes, we arrive at a one-parameter theory of the particle's behavior. The parameter is usually called F, capital F or small f in different papers, and it has the dimensions of mass. As you'll see, the masses involved are quite large on normal particle physics scales, indicating possible connections to very, very high energy interactions and unification scales, and in the context of cosmology, very high temperatures where the dynamics comes into is set. So, roughly speaking, below F, it acts like an axion plus this coupling getting fixed. Above F, you have a richer dynamics. So, as I said, this F is associated with the mass scale at which the potential T-violating effects first arise, when that coupling constant becomes effectively constant rather than something that can change in response to perturbations whose magnitude is F. So here is it a bit more formally. This is the way we encode the properties of quantum fields. There's this term tells you how the thing propagates, so it just tells you it's a particle that obeys the laws of relativity, and this tells you what its mass is. And I mean, this tells you that it has a mass in the context of Lagrangian dynamics, and this is the numerical value of the mass. It's associated with the strong interaction, and so we have lambda QCD, which numerically is about 100 MeV, million electron volts, appearing to the fourth power, and then F squared in the denominator. That's the mass of the axion squared. And then we have its interactions with matter, which have a 1 over F altogether. So the larger F, the smaller the mass of the axion and the weaker its interactions. These interactions are, if you're not familiar with quantum field theory, just think of this as a way of bookkeeping the possible interactions of the particle. Basic question, what is A? A is the axion field. So A is the quantum field that creates and destroys axions. It's similar, very similar in spirit to the electromagnetic field creating and destroying photons, the quanta of electromagnetism. So different quantum fields have different symbols associated with them. This A is a function of space and time, and here, and it indicates the field that creates and the quantum field that creates and destroys axions. And this is how the field interacts with other fields. This is the gluon fields that participate in the strong interaction. This is the electromagnetic field, F mu nu in relativistic notation. So this contains both electric and magnetic fields. And these are the quark fields. So the up quark, the down quark, and other fields, they also have masses. And these are the lepton fields like electrons, muons, and so forth. Another way of thinking about this that's more animated, maybe, in the sense of visual and tangible, that you can get easier to map your, think about in some ways, is in the language of Feynman diagrams, that a FF dual or FF twiddle coupling that you saw there is a coupling of A to 2 photons, because the electromagnetic field has quanta that are photons. So it's a coupling of the axion to 2 photons. Then we have the coupling of axion to 2 gluons. The gluons are strongly interacting, so we don't see them as free particles, but they organize themselves. They're found within things like protons, neutrons, and nuclei. And so the axion couples to all those kinds of particles through its coupling to gluons. And then we have these other couplings to electrons. So again, in the language of Feynman diagrams, it's just this little vertex, and another kind of coupling to hadrons through quarks. And those are all the interactions. So these are pictures, these Feynman diagrams, or they have the same information as the Lagrangian, and they when you put them into the rules of quantum field theory, they tell you everything that there is to be known about axions. They're particles that have spin 0. It turns out quite a small mass, and weak interactions that are of a very precise form, according to the theory, with the different components of matter. So let me spell this out a little more concretely in one case that's particularly relevant to interesting experiments, the electromagnetic part. It not only motivates several of the ways of searching for axions, but also the same equations, it turns out, arise in condensed matter physics, which to me indicates that we're onto something very beautiful with these equations, because they arise naturally, of course, with different values of the mass and the other parameters, but with the same structure within other states of within particular states of matter. So let me spell out that. So that Lagrangian, which previously we wrote as the coupling constant times the axion field times FF dual, we can, with the electromagnetic field, FF dual is just a relativistic notation for E and B fields. So this is just E dot B. And then we can go through the formalism of Lagrangian analytical mechanics to derive from the Lagrangian equations of motion. And these are the equations of motion you get. So this tells you in a very precise and explicit way how axions interact with electric and magnetic fields. So some noticeable effects, for instance, are that this first law is Gauss's law. Normally in I've left out other sources of charge and current. This is just the axion contribution. So normally this would be in Maxwell's equations, you'd have the density of charge on the right-hand side. So we can say that in the presence of a magnetic field, a spatial gradient in the axion field induces charge, where by charge, I mean the thing that electric fields tell you is charge, what electric fields see as charge. So axions can induce charge density in space in the presence of a magnetic field. Also, if axions are varying in time, then you get a contribution to the curl equation for B, which normally would be a current. So this says that time-dependent axion fields, which one has in axion cosmology, as you'll see, in the presence of a magnetic field, induce currents, and those currents will further produce magnetic effects. And they also induce currents that in the presence of electric fields instead of magnetic, they induce currents that are perpendicular to the electric fields. That's a kind of Hall effect. So all of these are things that either for real axions motivate different kinds of experimental arrangements, and in the case of emergent axions, give rise to different observable effects. And here I'm just saying the same thing in a different way. In the presence of a background magnetic field, an axion field mixes with the photon and can pump energy and current and charge into electromagnetic fields. And a creative activity is to add materials, including boundaries, to encourage the pumping. That's called designing experiments to detect axions. The other couplings are the couplings to fermions, and their main effect is to induce electric dipole moments in nuclei. When the axion field, the role in life of axions, remember that its original motivation was to explain why the dipole moments evolved to zero. But if the axion field is not at its minimum, if that field is fluctuating, therefore it induces non-zero electric dipole moments, and that is its key physical effect regarding coupling to fermions. And okay, so now topic 3, why cosmology needs dark matter. This would appear at first glance to be totally unrelated to anything we've talked about so far, but one of the glories of this subject, and to me a real hint that it's on the right track, is that it turns out to be extremely relevant. So I'll briefly introduce the subject of dark matter, which is an enormous subject in itself. But I just want to introduce enough to keep the motivation going. So many astronomical and cosmological observations point toward the existence of dark matter. What's really observed is not any kind of matter. That's, in a way, that's the point. That's why it's called dark. Dark doesn't mean that you see black clouds in the sky. In this context, dark matter means something that is totally invisible. It doesn't emit light, it doesn't absorb light, it doesn't do anything that's been observed so far except gravitate. So what's really been observed is not this matter at all, but kind of excess acceleration in different circumstances, or to put it a different way, more gravity than there should be if you ascribe gravity to the existence, to the effect of the matter that we see that generates gravitational fields. There seems to be some other kind of matter that we don't see that's also exerting gravitational influences. There are many, many different lines of evidence that lead to this conclusion, and one could easily give several seminars or colloquia on different lines of evidence. They all point in the same direction. Let me just show one that's particularly compelling and visual and beautiful. This is the phenomenon of gravitational lensing. When you look at galaxies that are behind other clusters of galaxies, so here you're looking at these galaxies through a cluster of galaxies that their light has to travel through to get to us, you find the general relativistic effect of bending of light in a really dramatic form, that it's like looking through the bottom of a soda bottle, a glass soda bottle, where the image is totally distorted. You see many copies of the galaxy, and this is called gravitational lensing. And you can study quite a bit about how the images have been deformed, how big the effects are, how well they're localized, and things like this. There's a lot of information in these kinds of pictures. And here is the kind of explanation that works very nicely. If you include extra matter, that is, you're looking at a galaxy, through that, that's in the background of another cluster of galaxies more nearby. The light, according to general relativity, is bent by the gravitational fields associated with the matter in this cluster. And that's why you can see several images that have taken different paths. And this works beautifully if you supplement the amount of gravity that you can ascribe to the objects we see by a factor of 6, roughly, and a smooth distribution of some other source of gravity. That's the dark matter. Now, as I said, there are that already is a remarkable phenomenon, but there are many other phenomena that point in the same direction. If you look at stars and gas clouds on the fringes of spiral galaxies, you see that they're revolving around the spiral galaxies faster than should be, than can be ascribed to the stable orbits of objects under the influence of this kind of matter you see in the galaxy. But if you multiply by a factor of 6, then it works. Then they're moving with the right velocity. Also in the early universe, that we need this dark matter to develop structure that forms into galaxies. Also to bend light enough from the microwave background. Many, many lines of evidence, all pointing in the same direction. So I think almost all astronomers would agree that there's compelling evidence for this unknown kind of, hitherto unobserved kind of matter that's seen only through excess accelerations. We know what it weighs, and we'd like to find what it is. We have some important information as a result of now of decades of work on this problem about what it isn't. We know it isn't anything in the standard model. Most potential things that are in the standard model, quarks, photons, electrons, even in bound states, so they're neutralized, they still interact much too strongly, and astronomers are very good at detecting any kind of ordinary matter, and that's ruled out. It's too dark. Neutrinos were thought for some time to be a potential candidate because they do interact very, very weakly with ordinary matter. However, they don't work. Now we know enough about neutrinos to know that they don't contribute enough mass density. And in any case, they don't have the right properties. They don't lead to galaxies forming in the way that they're observed to form. They are this is a little more technical. They are so-called hot dark matter as opposed to cold dark matter. I'll come back to that in a moment. We know that it's not primordial black holes. We know that it's not. Another leading competitor to axions in the particle physics community is something called WIMPs. These are weakly interacting massive particles, widely speculated to be associated with supersymmetry in particle physics. But since supersymmetry did not get discovered at the LHC, and also many searches for WIMPs as dark matter have come up empty, people are turning, so they've been excluded in much of their parameter space. And part of the reason for the explanation, or part of the explanation for why axions are getting more and more popular is that WIMPs are disappointing so far. Okay, we also have important clues about what it is. As I've mentioned now several times, we know that what we don't see is telling us that it's like the Sherlock Holmes and the dog that doesn't bark. We know that it doesn't interact very much. So that's a clue as to what it is. It has to be something that has very feeble interactions, can't be any of the particles we know about, and it has to be cold when it decouples. This is a little more technical. It has to do with how these particles are produced in the early universe. So in general, particles are in the Big Bang at first, when everything is hot and dense, particles are interacting very strongly with each other, and even weakly interacting particles get produced a lot. But eventually, as the universe cools and the matter gets more dilute, the interactions turn off. We call this decoupling. And when a given kind of particle decouples depends on, and its properties when it decouples depends on its interactions, and its effect on the subsequent evolution of the universe depends on whether the particles are moving fast or slow. That affects how they move other kinds of matter and goes into the theory of galaxy formation. And when you work that out, you find that you want your dark matter to be cold when it decouples. And so those are basically the only things we know about dark matter, that it has very feeble interactions and that it's cold when it decouples. Cold meaning that it's moving much slower. The particles involved are moving much slower than the speed of light. Okay, so that's a very, very superficial and quick introduction to dark matter. Now I want to say why axions can make dark matter, or how they make dark matter. And it really goes back to this picture. According to the theory, we have a field that has an energy minimum down here, but it also has a nearly flat direction. That's what the symmetry requires. And that nearly flat direction is the direction of axions. So in the early universe, you start basically with a random value of the axion field. The angle here is not determined, and a high value of the field, because the field is highly excited. There's a lot of energy in it, but as the universe cools, it rolls down and cycles around, and the residual motion is the axion background, and you have at the end of the day, a successful theory will have small residual oscillations, so that the observed value of the coupling constant, when it effectively becomes constant, is close to zero, as was the motivation, but the residual vibrations will turn out to be enough to supply the dark matter. So there are two distinct scenarios for how this might happen, depending on whether the field settles down before cosmic inflation occurs or after cosmic inflation occurs. Maybe in view of the time, I shouldn't go into too much detail about this, other than to say, if the field settles down after inflation occurs, then all possible initial states are equally likely. All possible initial angles are equally likely. And so you get random values of the axion fields today on large scales over the universe. And this, because we have the initial condition, although random is over the whole universe, is you can take the average, and so we get a definite prediction for how much axion dark matter gets produced as a function of the one unknown parameter f, and the calculations show that something close to f of 10 to the 12th GeV is what we need to get the observed dark matter density. Now, it's very remarkable that because observations constrain f to be greater than 10 to the 10th GeV, I'll spell this out a bit more later, and 10 to the 10th is not very different from 10 to the 12th, it's hard to avoid significant axion dark matter if axions exist at all. So even though axions were introduced for an entirely different motivation, it turns out that not only do they have the right properties to be the dark matter, but they get produced in the right amount to be the dark matter. So if they exist at all, I think it's hard to avoid the conclusion that they are the dark matter, or at least contribute a very significant fraction of the dark matter. The other cosmological scenario is that inflation occurs first. That means that the initial place of the field is the same throughout the whole universe. It turns out the whole universe expanded from a small patch, and that patch had a given value, and then that value takes over the whole universe. So then the amount of axions that are ultimately produced depends on where you started. Okay, it's always the case that you settle down to oscillations around zero, but the magnitude of those oscillations depends on how much energy was in the field. And now it's possible to have larger values of F, so smaller masses of the axion and weaker couplings offset by a kind of coincidence that the initial value was unusually small. I didn't say it, but let me say it now, that the end density of axions is proportional to F and to sine squared theta 0. So in this case, we need to consider that different parts of the universe that inflated, got separated by inflation, have different values of theta 0, and we only live in one particular corner of the universe with a special value of theta 0, and so most values of theta 0, if F is larger than 10 to the 12th GeV, will give axions that contribute much more dark matter than we have in our universe, and so our universe would be dominated. Those parts of the world are dominated by dark matter to such an extent that you couldn't have formed complex structures, let alone astronomers. So those effectively can't be observed, and so a selection effect tells you need a small value of theta 0, and once again you're led to the conclusion that axions, if they exist at all, pretty much have to be the dark matter. Okay, so that was, I realize, a very condensed presentation, but let me just restate the bottom line, which is that if axions exist at all, which we're strongly motivated to think they do because of fundamental physics, then they automatically address the dark matter problem in a way that seems to be very promising. So now let me move from sort of the motivations and theoretical context to concrete non-cosmological phenomena. So there are a number of astrophysical manifestations of this new kind of particle if it exists. Axions can be produced and emitted in astrophysical environments. If you go back and think about those Feynman diagrams, axions get shaken off when electrons or hadrons move, so they can be radiated. Then if they get radiated, even though that's a rare event because the couplings are small, they can escape from stars, whereas, say, photons have a hard time escaping from stars. So paradoxically, they perhaps, even the weakness is a strength as far as affecting stellar evolution. It gives a new mechanism of stellar cooling. And astronomers don't think they necessarily need new mechanisms of stellar cooling. So this is a constraint. And observations of red giant, neutron star, and white dwarf evolution constrain that this coupling constant F has to be greater than 10 to the 9th GeV or so. The coupling has to be so weak that these new mechanisms of stellar cooling don't upset the astronomers too much. Actually, there are some observations of stellar cooling that do seem to be anomalous. I would say they're not, and there have been claims in the literature that maybe you do need axions for evolution of horizontal branch stars, and that would be consistent with these other constraints, but I think those claims are not widely accepted, but are being checked out. We can also look for axions emitted from the sun. In fact, in the last year or so, there were experiments that claimed, the Xenon 10 experiment claimed to be observing axions, possibly a signal that could be associated with the axions emitted from the sun and impinging on the detector and producing excitations. It now appears that this was a radioactive background they didn't properly account for, but in any case, there are, that experiment was designed to do something else. There are very ambitious plans to make a kind of telescope where axions in a magnetic field will convert to photons, as we saw. So this is a kind of big tube that's filled with magnetic field in which axions can convert into photons, which then you observe down at this end. You point it at the sun. You need it really big, so because the axion couplings are weak and it's a small effect. But this is something that's seriously proposed as an experiment at CERN. You can see the scale of it. A smaller version of this has been up and running for years, the so-called CAST experiment, and also leads to the similar limits of this 10 to the 9th GeV for the F parameter. So looking at that positively, it shows that people are so interested that they're willing to go to great length to look for axions and search for them. Axions can convert into photons in the presence of a magnetic field, as I've emphasized several times. And neutron stars often have very big magnetic fields. That's what's responsible for the pulsar phenomenon. And we can look, therefore, for unexplained emission of X-rays, which would be axions in the universe, residual from the Big Bang, being converted into photons in the presence of a magnetic field. And this is something that's being very actively investigated, and there's even an interesting claim of positive indications. And this is an artist's conception of a neutron star with its magnetic fields and somehow axions being emitted from it. Not axions, but extra photons being emitted because axions convert in the magnetic field into photons. Finally, in this astrophysical chapter, spinning black holes can lower their energy by radiating light particles, reducing their angular momentum. And this is a very, very interesting effect called superradiance that allows black holes to build up an atmosphere if there are axions with very small appropriate masses. And black hole, there's a famous saying that black holes have no hair, but this would be an exception to that. They could have axion atmospheres, and that would affect their properties. And this is, again, an active area of research. There are some constraints on axions based on this, but also ongoing searches as we learn more about black holes to see if there's such an effect. Axions also have effects within terrestrial laboratories where we don't have to look out to the sky necessarily. Let me mention a few of those. Exchange of axions could lead to new macroscopic forces. The range of an interaction mediated by exchange of a particle is inversely proportional to its mass. So if you have light enough masses, they can mediate longer and longer range forces. Photons, of course, give you infinite range forces, for instance. But axions would generate forces depending on what F is on scales that range from fractions of a centimeter up to meters. And beautiful experiments have been done to look for such new long-range forces. And they continue to be done. Another interesting effect is light shining through walls. You can have photons that convert into axions, and then you put a wall, and if photons that haven't converted get blocked out, but if the ones that have converted to axions can move through the wall and then convert downstream into photons that you observe. And this is another kind of experiment that people have mounted and continue to mount. Let me turn now to what I think is probably the most promising direction, and which brings together the fundamental physics and the cosmology. This is the so-called Axion haloscopes, which now is not looking for astrophysical sources or for terrestrial sources effects, but trying to detect directly the axions which make up the dark matter halo around our own galaxy. One experiment is called Abracadabra, and it's very, very simple in concept. You have a large magnetic field, and as I've said, I've mentioned before, if you have a time-dependent axion field, it acts as a current. The current, in this case, would generate a time-dependent magnetic field, according to Ampere's law, and you can look for that time-dependent field as a way of searching for the axion halo very sensitively using squid technology. So this is the idea of Abracadabra. At present, a prototype is built, and there are ambitious plans to make things like this on the scale of several meters over the course of coming years. The Casper experiment is based on the fact that the axions induce time-dependent electric dipole moments, and if in the presence of an electric field, those electric dipole moments will act effectively like magnetic dipole moments. They will have the same dynamical effects as ordinarily magnetic dipole moments will have. And so you can use the techniques of magnetic resonance to search for those electric dipole moments. You simply use an electric field instead of a magnetic field and see if there's a coupling of that kind. Well, this is a little more detail on those experiments. If you use appropriate materials, you can do quite well, and this is a very active area of research. Another general class of approaches is based on converting axions to photons and then detecting the photons using the techniques of microwave engineering or with suitable modifications. So this is basically addressing the same kind of problem that Hertz originally faced in the 19th century when he was trying to test Maxwell's equations. You know the equations. You're trying to produce the fields that and detect the fields that the equations predict. And so it's a creative branch of engineering, if you like, or physical engineering to design the suitable antennas. So let me go back to that for a moment. So the Axion field is predicted to vary. Well, the Axion mass is not zero, unlike the photon mass. And so a result of that is that for a given energy, a given kinetic energy, if you like, a given frequency, the Axion field has a much weaker spatial dependence, a much slower spatial dependence than an electromagnetic wave. So the Axion waves vary for a given energy or a given frequency, vary more slowly in space than electromagnetic waves. And so if we want to get enhanced emission by resonance effects or efficient coupling, we need to address this mismatch in the spatial profiles so that the modes can match better. Or putting this in the language of relativity theory, where we have energy and momentum, we want to convert an axion, which has a mass and a very small momentum, a cosmic axion, it's cold, as we said, into a photon, which has in relativistic notation, a frequency equal to its momentum. So this doesn't conserve momentum, obviously. So we need to do something else in order to make it work. And there are different strategies. One is to modify the photon by putting it in a cavity. And then matching the cavity modes. So by having an appropriate cavity, you can have, very roughly speaking, a photon mass. More accurately, you find that the spatial variation of a mode can be much slower than it would be in free space for the corresponding frequency, and therefore it's a better match to the Axion source. And this is the principle behind the most advanced experiments, the so-called ADMX experiment, which is now quite a mature experiment that is actually the only experiment that's presently capable, that's presently sensitive enough to detect cosmic axions in of any mass, so of any value of f. The weakness of this experiment, unfortunately, is that, or the challenge of this experiment is that it can only sample very small slices of the parameter space, a very narrow range of frequencies or a very narrow range of f at a time. So you have to tune it like a radio receiver, and it's a slow process. People are using ingenious ideas to speed up the process, but so far the results are limited, but this is a very, very active and promising direction of search. And MADMAX is a slightly different strategy, where instead of using a cavity with conducting walls or superconducting walls, you use dielectric plates to modify the photon dispersion. And this is also under development. And then finally, there's the plasma haloscope, which we've been working on, and I think, well, I'm prejudiced, but I think is the most promising direction. It's based on a very simple logic that, as we said, the fundamental problem is that there's a mismatch between the massive axion and the mass zero photon. And we need to do some electrical engineering. One way is to do surgery on the electromagnetic field, so to speak, introducing appropriate inhomogeneities. But another way is to give the photon a mass. Then we can not have to cut things off in space, and that gives us potentially larger volumes to work with, and introduces different kinds of challenges and different opportunities. So there are several situations in which photons acquire a mass. Inside a superconductor, famously, photons acquire a mass, and most of the phenomena of superconductivity can be understood as consequences of exactly that. But unfortunately, to do the conversion of axions, we want to have large magnetic fields as a catalyst, and that is not compatible with superconductivity. Inside plasmas, photons acquire a mass, but the usual kinds of plasmas one thinks about, astrophysical plasmas or plasmas in the sense of plasma physics, are hot gases, and they are very hostile environments for detecting small signals, and so that's not so good. However, there's another kind of plasma that's very well known among certain communities in physics, but maybe not in the general public or in other communities, that there are plasmas inside metals. The electrons inside a metal are effectively free charges that can move around, and so that sort of is the definition of a plasma. However, it turns out that in metals, the mass that you get is too big for axion purposes. Semiconductors are being explored. We're actively where the plasma mass is less, so that's interesting and is under development. But maybe the most advanced, and I think especially interesting to this audience, is the possibility of using metamaterials. So very roughly speaking, you're taking the metals and making the density of electrons much, much less, and that reduces the plasma frequency. That's the very, very intuitive hand-waving explanation, but of course, you need to do better if you're actually going to design experiments. So the plasma frequency is determined by two factors: the effective electron density and mass, and we have wires that are containing electrons that interact with each other and set up a plasma by inductive coupling. And this is, I just wanted to show a little picture. Sid will say much more about this, I believe, but this is the prototypes are actually being built and tested out to see that the theoretical description of this kind of obscure corner of engineering actually works, and it does, and then verifying old experimental results and thinking about how to build on them for purposes of axion physics. And finally, I see I've already gone over time, but I hope you forgive me. It's still managed to be very superficial. There's a lot of ground to cover, I'm afraid. Let me very briefly mention axions. Axions in quotation marks. So these are axions that are not connected to particle physics and fundamental interactions, but things that obey the same equations with different values of the parameters that emerge in certain states of matter. So those are emergent axions. And another thing that's commonly mentioned in the literature are axion-like particles. These are speculative, even more speculative, I should say, possibilities where you have where you, whereas the axions that I've been talking about are a one-parameter theory, you can introduce more parameters just by hand, making the mass and the couplings be independently dialable, and those are called axion-like particles. And they're very popular in the literature because experiments can put constraints on a much bigger parameter space than just a straight line if you have axion-like particles. And well, they're also less compelling, but not entirely unserious motivations for axion-like particles. Anyway, so ideas and equations of axion physics have suggested and continue to suggest new effects in advanced materials. I'm very proud of this paper. This goes back to the early days when I suggested that such a thing could be possible, and then it's basically realized in topological insulators. And these effects, predicted effects, have been observed in quite wonderful experiments. And people are exploring possibilities. If you have quasi-particles that match the quantum numbers of axions, they can mix. We've been talking about how axions mix with photons, but they could also mix with other quasi-particles inside materials, sometimes even without needing external magnetic fields as catalysts. So this is an ongoing creative activity to try to identify quasi-particles with the right quantum numbers in appropriate materials to make yet another kind of axion antenna, potentially. And well, I won't go into details of this, but this is one of the proposals for making axions, and playing with these ideas has led to a thriving little cottage industry of condensed matter physics, where people are designing new materials in creative ways that have new kinds of quasi-particles, and it's stimulated a lot of creative work. Let me end by quoting Heinrich Hertz, whose name came up in several connections here, and he faced the challenge of showing that Maxwell's equations are actually a description of nature, and design new kinds of antennas to do that, and change the world in doing so. Now I think we're faced with a similar problem, and we have equations that are suggested by fundamental physics that crop up in unexpected places that have led to very, very interesting investigations that couldn't have been anticipated, and a potential explanation of the dark matter of the universe. So I'll just close by reading this quotation from Hertz, which is one of my favorite things in the scientific literature, which is that one cannot escape the feeling that these mathematical formulae have an independent existence and an intelligence of their own, that they are wiser than we are, wiser even than their discoverers, that we get more out of them than was originally put into them. So let's hope that keeps happening. Thank you.
Thank you so much, Professor Wilczek. So now the talk is open for questions. Let me start maybe with the first one. So speaking about plasma haloscopes, you mentioned that in order to tune the photon mass, effective photon mass to that of the axion, one needs to choose properly the period of the wire medium. But still, my question is the following. Since we do not know axion mass precisely, so it looks like we need different periods in that structure.
That's right. We need to be able to. It's like we have a signal from some radio station somewhere at a specific frequency, but we don't know what the frequency is. So we have to design our receivers or antennas so that they can be dialed, so that we can sample different frequencies. That's right. Yeah.
Yeah, okay, clear. And then
I should answer one question that came up in the chat that I didn't have a question I didn't have a chance to address, which was from George Al-Kahali. Do you think axions can explain the anomalous magnetic dipole moment of muons? Well, that's an interesting subject. First of all, I'm not sure. You may have seen there was a widely covered announcement from CERN recently of a more accurate measurement of the magnetic moment of the muon that disagreed with certain theoretical predictions that were made in advance based on the standard model. That the agreement is at the level of a part in a billion, but there might be a discrepancy at the level of a part in a billion. And that could indicate physics beyond the standard model, because the standard model may not be giving the right value of this very precise measurement. However, the theoretical calculations are a little bit shaky, especially when it comes to the contribution of hadrons to the anomalous magnetic moment through vacuum polarization of photons. And at the same day, on the same day that the experimental result was announced, a new theoretical calculation using high-powered computers to do the strong interaction part was announced that agrees with the experiment. So it's not clear that there is a discrepancy, but if there is, it's still unlikely that axions can supply the discrepancy if it exists, because their coupling is probably too small. You need well, maybe the effect isn't as big as originally reported, in which case maybe axions are responsible for it. But if it's not zero and is as big as originally suspected, then axions are not, I wouldn't say are a promising explanation. There are papers about it that address this in detail, and I think they reach the conclusion that it's not impossible, but very difficult to use axions. You probably need some kind of axion-like particle, and then you have to explain how it escapes these astrophysical limits and things like that. So it's very difficult.
So I see another question in the chat from Timur Sidov about renormalizability of the theory, which does it hold in the presence of
renormalizability of the theory hold in the presence of axions and axions-like particles? Well, the effective interaction of the axions is not renormalizable. However, if you embed the axions, as you do in the full theory, into a scalar field where they are essentially the phase of the scalar field, and the field also as a magnitude, then you can implement all this within the context of renormalizable field theory. So it's a very respectable kind of quantum field theory. It's really is a very, very minimal extension of the standard model, which uses the same ideas plus an extra symmetry to explain something that within the standard model appears to be quite mysterious, why this allowed coupling is so small, and does it in a very economical way. And so, but the short answer is you can implement all this within the context of renormalizable field theory very easily. Yes.
Thanks. And maybe a bit naive question about astrophysical part. So assume the axions do supply dark matter, but then how to explain that the dark matter is mostly concentrated in the vicinity of the center of the galaxy. So the astronomists are mapping, like drawing the maps of distribution of dark matter. How this can be explained?
Well, the only important interaction for astrophysical purpose, for cosmological and large-scale astrophysical purposes, is the gravitational interaction. So what happens is that in the early universe, you have small inhomogeneities that grow as a function of time due to gravitational instability. And the question, well, what happens according to the numerical simulations and theory is that the dark matter just self-gravitates and forms clumps, and it's actually the ordinary matter that we see as galaxies actually falls into them as kinds of impurities. The dominant source of matter by a factor of 6 or so is the dark matter, and really the ordinary matter falls into it. Now, that leaves the question of why the dark matter is kind of this diffuse cloud while the ordinary matter makes a much more compact galaxy. And the reason for that is that ordinary matter, well, so if you have things that are collapsing gravitationally, if they don't have ways of losing energy, they just fly through each other. They fly towards the gravitational potential minimum, but then just keep going and slosh back and forth. They can cool off a little bit because of higher order gravitational interactions, but basically they form a diffuse cloud, whereas ordinary matter, as it congeals, can emit radiation, lose energy, so to speak, and continue to collapse and form tighter structures. So this, according to the simulations, is how galaxies form and fragment into stars and planets and so forth. So in the case of so in both cases, the essential process is gravitational instability. The gravitational instability of dark matter is larger quantitatively because there's more dark matter. However, the dark matter itself can't lose energy, and so it forms diffuse clouds, whereas the ordinary matter that falls into it can lose energy, can cool off, and form galaxies and the other astronomical objects we observe. So I hope that answers your question.
Yeah, thank you. So I see 2 more questions in the chat. So colleagues, I encourage you to raise a hand. You can also ask by voice if you wish. So the question from Alexander Andrianov. What about Axion stars and Axion condensation?
Well, yeah, there are possibilities of Axion stars that are, in fact, there's quite a literature about them. They are not stars in the sense of, they're not very analogous to ordinary stars. They're much more diffuse, tenuous kinds of objects. But they can affect the signals because they're although they're tenuous, they're less tenuous than the background dark matter, so that they can lead to enhanced conversion of photons, for instance, or other effects. But so people are very much interested in that. I don't know that there are any very dramatic results that have emerged so far, but it's part of understanding the distribution of dark matter to understand these kinds of condensations. They're often called mini clusters and clusters. You want to see if the predicted distribution of dark matter matches what's actually observed by astronomers, and that's so far it seems to work very well.
Right. So another question from Valery Kozin. Does the existence of axions have some consequences for the running couplings in the standard model?
Not in any very direct way. the simple ways, the most straightforward and minimal ways of implementing this kind of dynamics, the Petre-Quinn mechanism, involves fields that don't really participate to first order in renormalizing the gauge couplings. Now, if you try to embed, so that's the zeroth order answer, and maybe the first and second order answer. But if you try to embed these ideas in more comprehensive frameworks with granularification or string theory, then there become indirect connections between Axion parameters and running of the coupling. But they're very speculative, and there's no simple conclusion that emerges. So the basic answer is there's no direct connection, and any connection is quite speculative.
So another question about, you discussed two scenarios, whether the axions separate from other interactions before the inflation stage or after the inflation stage. So a bit naive question. So if axions separated after the inflation, so we can imagine several like domains in the universe with different values of axion field with different phase. So I can imagine that there should be something happening at the domain wall between these two domains. So it's like H states between two topological insulators, I would say.
Well, this field is an angular field, so it doesn't really form domain walls. The domain walls would be if you had, if you had a few preferred directions and you could get stuck. But this field doesn't have that kind of structure. There's a unique ground state and then a continuous variable around that. So you can't, well, I'm oversimplifying a little bit, but basically in appropriate models of Axion physics, the domain, there aren't stable domain walls. What is true is that the angle varies, the initial angle varies over the universe, and the characteristic scale of that variation is large on laboratory scales, so to speak, but not on astrophysical scales. I think it's roughly, I don't remember exactly, but it's smaller than the scale of galaxies. So any reasonable size sample of the universe for cosmology will average over the initial values. So you get pretty much a uniform density on cosmologically interesting scales.
So I see another question in the chat from Jebin Lerosh. The astrophysical search using birefringence effect via G-lensing and Faraday rotation compare with underground detectors. Which approach has better significance?
Oh, well, I'm gonna not attempt to give a quantitative answer to that. Of course, it's discussed in the literature. I think the birefringence is subject to many uncertainties about what the magnetic field, cosmic magnetic fields are. It's also a very small effect, and other astrophysical effects can affect polarization. So I think that's a tough one. More, how should I say? So I'm not sure what you mean by underground searches, but I think you probably mean the cavity searches. And so I think the cavity searches will give much more definitive results and are much more promising. I'd be happy to be proved wrong, but that's what I think.
Yeah, thank you so much. So I do not see other questions from the audience. So maybe someone, if someone has questions, please raise the hand. So maybe I would ask one more question also related to astrophysical part. So as far as I know, there are several attempts to modify somehow the equations of general relativity, at least to partially explain the anomalies in the motion of stars in the galaxies, and so on. So what do you think about these approaches? Can they at least partially explain something?
Well, not much. I mean, the cosmological scenario based on cold dark matter works very, very well. I mean, people have done very elaborate simulations of formation of galaxies and things, and as I said, there are many, many independent lines of evidence that are consistent with the existence of dark matter in the form of particles. So I mean, general relativity has the feature that, because of the principle of equivalence, if you like, or the universality of gravity, that you don't have to know about the details of what the particles are in order to track how their gravitational effects. And so we can, with minimal assumptions, check out the effects of cold dark matter, and they just explain so many things about gravitational lensing, about microwave background radiation and homogeneities, about galactic rotation curves, about something called the bullet cluster, where you see the gravity separating from matter when two galaxies pass through each other. There are just many, many independent signs. And people have attempted to change relativity. I think it's fair to say that those attempts are extremely ugly and contrived. And at most, they're designed to explain one or two of these effects, but none of them come close to explaining all of them. So, I don't. Well, you know, maybe there's some as yet undiscovered way of generalizing, of changing or generalizing general relativity that will resolve all our problems, but it sure looks like it sure looks like another particle will do the job, and attempts to do it the other way they've been very energetic, and people, lots of people would like to be the next Einstein, but so far, I would say they're not impressive. Yeah.
Thank you. So I see the question from Mikhail Portnoy. Please, so now you can unmute.
Hello. I visited you in Princeton in '99 in December. The best of Misha Fogler, and you were very excited about anyons at that time.
Yes.
It was we dined with Dyson and Anderson and anyons, axions. It is a philosophical question. What will you be excited next? Probably not.
Well, I'm still excited about anyons. As you may know, after kind of basically 40 years of waiting, they've been observed, and they're becoming a thriving chapter of condensed matter physics and maybe of technology. They're proposed to be used inside quantum information processing. So that's really thrilling. I'm glad you mentioned it. And so it also shows I've been right before. So maybe we'll get lucky again. But Okay, well, this really is a philosophical question, and maybe I shouldn't be discussing it in terms in front of this audience who expected to have a physics lecture. But I'm very excited about understanding the nature of time in quantum mechanics, and I'm actually very excited about understanding. This will sound crazy, but I don't think it is. I'm very excited about understanding how mind emerges from matter. And specifically how self-awareness arises from logical and material structures. So that's what I'm really excited about now.
Thank you very much.
All right.
Thank you, Mikhail. So now another question from Andrei Volodka. So will the Weinberg angle change in the presence of axions?
No, well, not significantly. I mean, some level, yes, but not in a quantitatively significant way.
Mm-hmm. And so two more questions, like very short and like general. So from Galina Vlasova, when can we get the universal equation of the universe? And can we?
Don't hold your breath. So like, I don't think we're very close to it. I don't even know what it means exactly, but well, let me try to answer it in a constructive way. I think the universe as we observe it is very complicated in two ways. One is that, say, within the standard model, which encapsulates a lot of what people have observed over centuries of careful investigation, and we find that there is a whole mess of particles with different masses and in detail messy couplings when you come into the weak interactions and their decays to do justice to all the details. And I don't think we're very close to explaining all that structure. So when you ask when, I have no idea when. Now, if you change the question to say, could we get equations that when supplemented with some scenario about the evolution of the universe and different kinds of couplings settling in, just as the Axion settled in, the Axion field settled in to fix a coupling constant. You fix the other coupling constants by evolution, and then you'll have other parts of the universe with different values. And so could you sort of talk yourself into a picture that you have some very fundamental equations, say based on string theory, which we don't understand either, but say then you would declare victory, I guess, even though you haven't explained a lot of the world as it actually exists, and then namely you haven't really explained the actual values of those masses and couplings and so forth. And then there's a third layer, which is even more hopeless, or which is that suppose you could explain all that, would it really explain how the world works? I would say it only explains very little about how the world works. It doesn't tell me anything about what human beings are like, or what frogs are like, or why flowers have the smells and colors that they do. So there's a whole world of emergent phenomena and complexity that I think is no universal equation of the universe that's within sight will address. So So okay, that's a long answer to the question, but the short answer is don't hold your breath.
Thank you so much, Professor Wilczek. Great talk, very inspiring for us. So I believe now we can switch to short presentation by Dr. Sid Marampunti. Okay, good. So thank you so much.
Well, it was a joy. Okay.
So now that you guys know what axions are, so how is it actually relevant to the kind of stuff you in metamaterials? So how do you detect axions in metamaterials? So the broad thing is that the biggest problem here is that it's an extremely tiny coupling. The axion the way axion couples to ordinary matter and light is extremely tiny. And there is a huge search space you need to cover to find the mass. Unlike other elementary particles where we had roughly an idea of where to look for, there is a much larger parameter space for the axion. So you need many different search techniques. So hopefully metamaterials can help with this because they can cover this large search space for the mass. So as Frank was saying, axions can convert into photons because there's so essentially an axion, you have a process in which an axion can convert into 2 photons in vacuum. But this process is hoping for that to detect the axion by decays is not a good prescription because the half-life of an axion is like 10 to the 42 seconds, which is longer than the age of the universe. So you actually have to do something active to induce the axion to decay, which is what many of the search strategies try to do. So one of the interesting things is that so this axion is extremely light. So if you think of actual units, it's all the best estimates. It will weigh at most like 10 to the minus 33 grams. So it's extremely light, but it also has to, as Frank pointed out, it has to make up all of dark matter if it's a good dark matter candidate, which means that it must be a huge density of it. To give you some number, there must be like 10 to the 18 axions per liter of space. And by liter of space, I mean literally everywhere, not just out there, but going through me right now, through all of you. So they never interact with us, but they can just pass through all of us, and there'll be a very high density of them. And this high density has an important implication. It means that it behaves as a coherent classical field. So it's literally like a field which is similar to everyday light. So you don't think of individual photons, but you actually think of classical light. Similarly, here you should think of the axion not as an individual particle, but you literally have like a coherent classical field going around space, like axion light, if you would like to think about it. So one of the important implications of this is that it actually modifies Maxwell's equations. It's not single photon effects. It's literally a classical microscopic field. So you have modifications to the coupling to the photon induces changes to Maxwell's equations. So it gives you these 3 additional terms here, B dot grad A and these 2 terms here. And all of the experimental searches on Earth try to use some of these effects. They don't even use all of these effects, only a subset of these effects. So for one of the important things to notice is the axion has a large de Broglie wavelength, which means that these terms just the gradient terms are just negligible on scales of the experiments done on Earth. So the only important term, so basically your axion field looks like some constant classical field and oscillating with some frequency. So the only additional modification to Maxwell's equations is this term here. So you have so it's G del A by del T times B. So it just modifies Ampere's law. So if there is an axion, if there are axions and if they are a component dark matter, it should just give you a modification of Ampere's law. So if you put in an magnetic field, the axion will induce an effective current in a system. And what the aim of our experiments, all the experiments done so far, is we need to find the frequency of these currents, of this current. And why the frequency? Because this frequency is basically the mass, because it's mc squared plus a very small kinetic energy, which you don't really care about. So, but if you know so that's the search strategy. You try to see that there is, you try to figure out if there is an oscillating current at some frequency, just but once you put in an external magnetic field in space. And this is called the inverse Primakoff effect. So instead of your 2 photons, you put in a static magnetic field, and that gives enough energy to generate real photons. So basically, you want to put in a static magnetic field, and that gives you a time-varying current, and you want to detect that time-varying current through whatever experiment you propose. And one of the important things is this coupling constant for this current. So that the magnitude of this current is extremely small. So this G can be like 10 to the minus 10 or even smaller sometimes. So many of the approaches which are only feasible need to use some sort of resonance. And that's so the ADMX, which Frank was talking about, essentially tries to use a resonance. So you try to build a cavity. So if you want a resonance for your for light, the simplest thing is you take a cavity, you put the cavity inside a strong magnetic field. And since we have axions just floating around everywhere in space, 10 to the 18 particles per liter, so there are axions also in this cavity. And once you switch on the solenoid, the strong magnetic field will cause those axions to turn into real photons, which will resonate with the cavity. And you will pass that through some electronics, and you'll hope to see some, you will see some power increase at some frequency, which is the mass of the axion. So you keep running your experiment at different frequencies, and if at a certain frequency, if you see some increase in the power, you know that that there must be a time-varying current which is being generated, which must be because of axions. Now you can already see the problem with this approach. Now the signal you generate has many factors in that. So it has some coupling form factor, and it's proportional to the volume. The larger your volume, the better your signal. It's proportional to the quality factor of your cavity, and then you have axion density and magnetic field. So the easiest things you're in control of is your magnetic field. You can double your magnetic field and get a factor of 4 in power. You can get high quality factors and you can increase your power, or you can increase your volume. So if you have a very large experiment, you can again increase your power. So this already tells you what the problem with cavities is. Since the cavity's frequency is tied to its size, so that which means that once you start getting into microwave and higher, or you start getting to high gigahertz frequencies, your cavities become super small. So you lose the power, and you do not want to lose power because you're dealing with things like octa watts, which are like 10 to the minus 20 watts or so. So you're dealing with extremely tiny powers. So you don't want to lose that physical volume. And in addition to that, cavities are difficult to tune, and the way they do it in the ADMX experiments is they use tuning rods inside the cavity, and they slowly move these tuning rods around to sort of get some tuning in the cavity, but you still don't get much of a tuning. So cavities are limited in that aspect, and you can already see this this in the search space. So the search space for axions. So the x-axis here is the mass. So you want to cover a large search space. So the different colors are different limitations of imposed already by known physics. So galactic astrophysics imposes that you must be above like 10 to the minus 6, 10 to the minus 7 EV, and then cosmology says that you must be below a certain amount. So you have that still gives you about 3 or 4 orders of magnitudes in search space to cover. And these red lines here, these red data here is current cavity searches. So you can see the current cavity searches have only been able to cover an extremely tiny parameter space in this whole process. And you can see that at 10 to the minus 4 EV is about 25 gigahertz, which is a centimeter. So once you start getting to higher than, once you start getting to these frequencies, your cavities will become super tiny. So it's not even practical to construct cavities at this range. So, but then how else do you do it, right? So there are future proposals about various different experiments which could try to probe it, but they're all hypothetical, and they're all in a certain frequency range, which are not very tunable. So metamaterials could actually help us overcome the limitations of cavity. And this beautiful paper by Pavel and others, they on wire metamaterials, you can see that you can get gigahertz, terahertz, optical. You can get a huge range of frequencies, and depending on the kind of metamaterial you have. So yeah, essentially you can since your physical size is no longer tied to your frequency strictly. So you're allowed to have large volumes and still work in microwave and higher frequencies, which is very good for your power output. So the essential idea is you just have like what we're working on is basically putting a wire metamaterial inside a big magnetic field inside a cavity, and then you have an Axion wind which is just going through the whole system. As soon as you turn on the magnetic field, you'll generate a time-varying electric field, a time-varying current, which will then resonate in this cavity, and then you'll hope to detect it. So this is the experimental setup, which I don't have a picture of the real setup, but this is the model setup, which is being built at Berkeley, where you have wire metamaterials, which are tunable in the sense that we're tuning them by basically changing the layers between by changing different planes. So that gives us some degree of tunability in the frequency. And with that, we used hope to cover a good degree of parameter space. For example, so again, the plasma haloscope is what we call it. And you can see that it can cover a wide range of frequencies, some of which is not accessible to any of the current techniques. And possibly with more interesting metamaterials, you could hope to cover a much wider class of the space with a single setup, which would be very interesting. Instead of using multiple different setups for different frequency, if we have a single approach which you could tune to cover a complete range of frequencies, that would be a game changer in the Axion search experiments. So just to give you an example of illustration of how this works, if you take a 2D simulation of wire metamaterials with a 16 by 16 grid of perfect conductors, radius of 0.02 and lattice spacing of 1, and you have different theoretical plasma frequencies, and you can find there's an actual plasma frequency of 0.2285 here. And then what happens is you're going to put the system in a solenoid. So that solenoid will effectively induce an electric current, a time-varying current through this whole system, and you should hope to detect it. So remember now here it's at 0.2285 is the frequency. So if you're well below the plasma frequency, dark means no intensity. So you have basically there is no, it's supposed to be reflecting. So it's like it reflects all the fields. So all the fields are coming outside. If you go well above the plasma frequency, all the fields go through. So again, I'm sure all of you are familiar with this in the field of metamaterials. Once you start going closer to the plasma frequency, you can start to see that there is a resonance in the system. And exactly at the plasma frequency, the whole thing just lights up, and sort of like an Axion antenna. And so this volume current is sort of picked up by this wire metamaterial, and now you hope to try to detect that with some readout system. This is a simple movie. So let me speed it up. So if you switch on the current, and you see that essentially there is a mode which is set up in the system. So what I've done is I've just switched on a time-varying current in this system, in this red region, and now there is a mode which is excited in the system, which is this huge volume mode you see over here. And at 60 seconds here, now I've turned off the current, and you can still see the mode is still resonating in there. And it is this mode which we want to try to detect with some readout mechanism. So now I'll end with saying that this is a partial wish list of the things as a challenge to the community here. That we want a system with we want a metamaterial system which is tunable over a large range, over, you can, let's say, from megahertz all the way to high gigahertz or even terahertz. It's even something which is partially satisfying, that would be great. Something which is macroscopic size, because you want to stay of the order of meter or larger, because if you go to very small sizes, you lose power. You want a very high quality factor, and you want an efficient antenna design to couple to this mode. And that would be interesting if there is a setup which could satisfy at least some of these requirements. And I think that's it. Yeah.
Thank you so much, Sid. Very interesting talk. The talk is open for questions. Colleagues, if you have any, please raise hands. So in the meantime, I would ask the following question. So you mentioned that in order to detect, you detect axion as some resonance in the spectrum which you measure. So I wonder what are the requirements on the signal to noise ratio? So do you need some extremely low temperatures or some other special conditions?
Right. So I'll give you an example. The ADMX experiment, which uses a cavity, it's run at cryogenic temperatures of a millikelvin. So they put the whole thing in a dilution refrigerator. So because even simple thermal photon noise can overwhelm the signal. So even just having free photons floating around at millikelvin temperature can overwhelm it. So they really, a signal to noise ratio needs to be extremely high, and so that's why they run the setup at extremely low temperatures. Yeah.
Thanks, Sid. So now I see a question from Pavel.
Yeah, thank you. Sid, can you please return to your nice formula for coupling to the resonator?
All right. So this is a coupling to the cavity. There is a slightly different formula for the resonator, but it essentially has the same factors. Yeah.
Yeah. I have a question over here. So this is coupling to the cavity. It includes volume, so on and so forth. But all we know that, for example, there is a Purcell factor, and Purcell effect. Then for some, say, time varying states in some cavities, you have this modification and so on and so forth. Reciprocally, in the excitation of some objects, it can be not really good cavity in a sense that it's localized field, but it may have very good Purcell factor. And actually in metamaterials, there were many examples when by designing of metamaterials, you can control precise the Purcell factor. In some sense, it means that you may have extremely small current, but as soon as this current is placed into medium with extremely high Purcell factor, the amount of energy extracted from the current, if the source is a current, is extremely large. Have you thought about not just applying a classical formula for the cavity, but thinking in terms of this Purcell factor or something related to this? Because we have seen many times that with some quantum sources, the people say are using optical antennas in order to extract more energy out of some quantum source. And at this moment, already Purcell factor may dominate over quality factor of this resonator. And basically, you have another degree of freedom to get more power out of it.
So I cannot, I'm not fully aware of the entire field, but I have not seen anyone talk about the Purcell factor so far.
Okay, so we can talk then, because it's also very closely linked to metamaterials area, and kind of it's also another degree of freedom which can be controlled, not only volume of resonator, numbers which correspond to the resonators with the help of metamaterial, but also this thing.
Yeah, that's interesting. I'll definitely follow up on that. Yeah.
Good. Thank you, Pavel, for question. Colleagues, if you have some other questions, please raise hand. So in the meantime, Sid, I would ask you about the diagram in axis GA gamma, interaction constant, and axion mass. So which you showed us in your presentation. This one. So are there any limitations from the bottom? So can we say that this interaction constant is definitely more than, let's say, 10 to the minus 20? Or there are no such limitations from the bottom at all?
So there are there are two limits. I think Frank can maybe give a better answer on this. I do not believe that. I think there is any limitation on the bottom, but maybe Frank has a better idea. There is a band of frequency. There's a band.
Yeah, well,
which is.
There's. I would say there's a soft cutoff when F gets to be the Planck mass.
Mm-hmm. Oh, right. Okay.
So that would be, I think that basically corresponds to the bottom of this diagram. If I see the numbers correctly.
It's It's
so 10 to the 19th.
Yeah.
10 to the minus 19th is really I think most particle physicists would be very reluctant to go beyond that.
Yeah, that's good. So we have finite area for search.
Yeah.
Max, can I ask another question?
Please, you're welcome.
Yeah, Sid, can we come to your slide number 4? Was it with Maxwell equations?
Mm-hmm.
And you killed some parts, yeah?
Mm-hmm.
So you explained us quite nicely, okay, why you are taking into account something which is in the square right now, yeah? And you threw away these other components, yeah? Have somebody tried to use these other two, because it may be some other conditions, say electrical field, under which you can use it, yeah? So I see there is a variation of time, and it means that something which you are detecting with axions right now, it means that A should vary with time. But if it's for some reason do not want to vary with time in vicinity of our observation, maybe another contribution should be tried to detect it.
Right. So you're saying that if the frequency is extremely small, such that yeah. So I as far as I know, I believe that there is no current running experiment which uses the other terms. There is no running experiment. The only running experiments are things like ADMX and others. There might be future proposed experiments, but so the main thing is that de Broglie wavelength. If you compare it to the Axion length scale, it's a factor of 1,000. Which relates them, which is why people think that, okay, the gradient if you're constructing this, experiments of this much size, then on that scale, the gradients really don't matter in the relevant scales you're looking at. But so I'm not fully up to date with all the future experiments, but there might be future experiments which probe the other terms.
Some of the experiments based on not on the coupling to the electromagnetic field, but on the coupling to spins, do use spatial gradients. That's something called the Casper-Wind experiment. But
so not in this context.
But not in this context. That's right. Not in the context of the electromagnetic field.
Yeah.
Okay, thanks, Sid. So just to sum up the discussion, so do I understand correctly that the wish list is to help with the design of, let's say, metamaterials which allow to probe Axion field in the form of some haloscopes, let's say. So
so it would go on.
I believe we can somehow assist, but just maybe need to be more specific. So if you can later send us maybe more detailed wish list, we will be happy to help, because the department is really huge, more than 300 people doing different aspects of metamaterials physics. So we'll be happy to somehow assist.
Actually, maybe I can also answer, because already a number of participants of today's seminar dropped already to 43. So probably right now, all the people who are really interested to help with experiments remains in the Zoom. So actually, probably the next step is that in 2 weeks, Frank and Sid, they kindly invited me to join very nice workshop in the area in this devoted to this haloscope topic. Yeah, I will attend this workshop, and I don't know if colleagues will allow at least say somebody else also to attend. I don't know if it's possible. Or say
yes.
one person,
definitely.
if it's possible, it would be really useful. Then after this workshop, we will have more understanding and more details about what is needed. And then we can make another small meeting, and already based on our knowledge of metamaterials, we will be able to provide something more. Because Maxim, right now, the story is the following, that we need to provide our knowledge to colleagues about metamaterials. Actually, there are tunable metamaterials, there are metamaterials which localize field with high personal factor, so on and so forth. These all effects of metamaterials are not yet taken into account in designs of these cavities. So as soon as we make reciprocally exchange all the knowledge which we have from both sides, maybe at a certain moment we will realize what is really needed. Yeah, because probably it's not a secret with SEED. Yeah, at very beginning, few weeks ago, we started from the fact that SEED didn't know many works about wire medium and the basic proposals of this plasmonic haloscope were based on John Pendry's work. Yeah, right now we discussed, and we already all know, but there is a little bit more than just one work of John. And right now, as soon as we will make more steps towards understanding, probably maybe, I don't know, we have in our lab many tunable metamaterials, tunable by light, tunable mechanically, tunable by some other things. Maybe very simple solution will appear. But okay, it should be simple solution, but freezable to very low temperatures. This is
that's an absolute requirement. You can't get around that.
Yeah, we need very low noise, very large magnetic fields.
Yeah. So Maxim, answering to your questions, we will provide you a little bit more information in 2-3 weeks time after the workshop. And colleagues, don't mind after this seminar today, the people can send me some proposals. If there are some active 1 or 2 guys, I will definitely nominate them to join the workshop if colleagues do not mind.
Please do, by all means.
All right, brilliant.
All right,
great.
Thank you so much.
Thank you.
Okay, thank you. I've got to go, unfortunately. We'll stay in touch. Okay.
Yeah, stay in touch.
Thank you for your talk. It was really important and useful. Yeah. And I sincerely hope for fruitful collaboration in the nearest future. So hopefully we will be able to emerge with 2 areas of purely theoretical physics and metamaterials and make something nice altogether.
Well, that would be beautiful, and I think it's entirely plausible. Yes. Okay. All right. Bye for now.
Goodbye.
Goodbye.
And thanks, Sid. All right. Bye.